Section 7.5 of your textbook covers the topic of linear inequalities in two variables, and more specifically describes the process of representing the solutions of those inequalities on the coordinate plane. Remember that for a linear inequality in one variable, such as x is greater than 4, the solutions are represented by a shaded portion of the number line. And in order to indicate those solutions, we first graph the end point, in this case 4, and then we shade one side or the other of the number line, starting at 4. A closed circle indicates that the end point is a solution, and this would occur when we have the symbols less than or equal to or greater than or equal to. And an open circle indicates that the end point is not a solution, and this is used when the inequality contains a less than or a greater than symbol. By comparison, for linear inequalities in two variables, such as y is less than or equal to x plus 5, the solutions will be represented by a shaded region of the coordinate plane. A boundary line is drawn which divides the plane into two regions, in the same way that the endpoint divides the number line into two regions in the case of one variable. And then one half of the coordinate plane, the half containing the solutions to the linear inequality, is shaded. The solid line indicates that points on the boundary line are solutions and is used when a less than or equal to or greater than or equal to sign are present, and a dashed line indicates that the points on the boundary line are not solutions, and this is used when we have a less than or a greater than sign in our inequality. Let's look at some examples. First example is to graph the solutions of the inequality 2x minus 3y is greater than 6. First, we need to graph our boundary line. The boundary line is found by replacing the inequality symbol with an equal sign and graphing the line 2x minus 3y equals 6. Probably the fastest way to graph this line is to graph the intercepts. The x-intercept occurs when y is 0, and therefore in this equation x is 3. And the y-intercept occurs when x is 0, and therefore in this equation y would be negative 2. Graphing those intercepts, 3, 0, and 0, negative 2, enables us to graph the boundary line. Note that the inequality contains a greater than sign, so our boundary line should be a dashed line, indicating that points on the boundary line, such as our two intercepts, are not solutions of the inequality. To understand why they are not solutions, we can simply substitute one of those points in as a test point. For example, take the point 3, 0. If we insert that point into our inequality, we obtain 2 times 3 minus 3 times 0 is greater than 6. This leads to the inequality 6 is greater than 6, which is false, indicating that the point 3, 0 is not a solution of the inequality, hence the dashed line. In order to determine which side of the boundary line we should shade, we'll test some other points. For example, try the point 0, 0. This point leads to the following when placed into the inequality. 2 times 0 minus 3 times 0 is greater than 6, or 0 is greater than 6. This is also false, indicating that the point 0, 0 is not a solution of our inequality. Since this point is not a solution, all of the points on that side of the boundary line are not solutions to the inequality, which means that we can shade the points below the boundary line, knowing that that half of the coordinate plane, all the points in that half of the coordinate plane, are solutions to the inequality. Just as a quick check, we could test another point. For example, the point 2, negative 2 is clearly on the side where we've shaded our solutions. If we place that into our inequality, we obtain 2 times 2 minus 3 times negative 2 is greater than 6, or 4 plus 6 is greater than 6, or 10 is greater than 6. This inequality is true, indicating that 2, negative 2 along with all the other points on that side of the boundary line, is a solution to the inequality. Let's look at another example. In this case, we're going to graph the solutions of y is less than or equal to negative 1/2 x plus 3. The boundary line then would be y equals negative 1/2 x plus 3. And in this case, because of the less than or equal to sign, we know that our boundary line will be a solid line. Since this equation is in slope-intercept form, we will graph using the y-intercept of 0, 3 as our starting location, and finding more points using the slope of negative 1/2. Starting at the point 0, 3, the slope indicates that we move down 1 unit and to the right 2 units to find another point. We can continue doing so to obtain some more points, and then we will graph a solid boundary line. Points on the boundary line are solutions in this case. For example, the y-intercept 0, 3, when tested in the inequality, leads to 3 is less than or equal to negative 1/2 times 0 plus 3, or 3 is less than or equal to 3, which is a true inequality. Now we just need to test one more point to determine which side of our inequality we should shade. The origin 0, 0 is often a convenient point, an easy point to test. Substituting into our inequality, we have 0 is less than or equal to 0 plus 3, or 0 is less than or equal to 3. Since that is a true inequality, the origin and all points on the same side of the boundary line as the origin are solutions of our inequality, and we can shade the lower region of the coordinate plane. For our next example, we'll actually look at an inequality that contains only one variable, but the solutions of these inequalities can also be indicated on a coordinate plane. For example, our linear inequality is y is less than negative 4. This means the boundary line is the line y equals negative 4. And recall that this is a horizontal line passing through negative 4 on the y-axis. Because we have a less than sign, we know that we need a dashed line for our boundary line. We'll draw it here, going through the point negative 4 on the y-axis. In this case, a test point really isn't even necessary because we know that we're looking for all the points where y is less than negative 4. So we can just shade below our horizontal line, knowing that all those points in that region are solutions of the inequality. Finally, if our inequality contains only x, we have such a situation as the following. For the inequality x is greater than or equal to 1, our boundary line would be x equals 1, which is a vertical line passing through 1 on the x-axis. In this case, our vertical line will be solid because we have a greater than or equal to sign in our inequality. Now to shade, we simply look at our inequality and see that we want all the points that are greater than or equal to 1 for their x-coordinate. That will be the points to the right of our boundary line. So we can shade all of those points to indicate the solutions of our inequality.